Thank you, Armando, for bringing me here. Thank you, Peter. It's always a pleasure to come here and interact with you guys. I can see the size of the audience increases every year, so that I suppose is a very good sign. So, I'm going to make a fair assumption here that most of us in the audience have looked at different alternative data sets, have used them to make different signals and strategies, have played around with a few machine learning techniques, are aware of at least the rudiments of what data analysis comprises of. What I'm going to do today is highlight a few places where I think we collectively as an industry might be erring, where there is more mistaken emphasis on certain areas, where there's less emphasis, right? And again, as in all advice, it cannot be uniform for everyone, right? If you go to left, I must tell you to come right. If you go to right, I must tell you to go left. So it's not uniform for everyone, but hopefully many of this would be widely applicable to this audience. The first point that I wanted to tell you is think of data and techniques separately, right? Do not conflate them. I often see that conflation. You have raw data that can come in terms of text and images, which seems to be the fad. Doesn't mean you can't get a lot of alpha from existing numeric data. But once you get this text and image data, it gives you one quicker insight, it gives you a differentiated insight. Those are two things happen, and you can process it using relatively more complex techniques, right? So somebody gave you a satellite image, you want to count the number of cars, you can use CNN and count the number of cars, right? Is it complicated? Well, there's a Kaggle competition on counting number of seals in a photo, you could do the same. But even that, you may not want to do it in-house. You could easily outsource it, and it would actually make sense for a lot of my clients, because our core competency lies in finance. It's not really in writing neural networks, right? And indeed, there are firms that can do it for you. Once the textual data or the unstructured data is brought into a numeric data, right? So you have numbers in Excel, you'll often find that sometimes the data is actually not big. It's actually quite small. So you'll have less number of points. And in many cases, you'll have a lot more columns than rows, right? So when I say it, I don't mean it. So if you look at the book Elements of Statistical Learning, the last chapter says P more than equal to N. If you did econometrics PhD in the last few years, probably you wrote some papers on it, so then you don't need my advice. But if you didn't do so, I would say be careful of this. When you choose, so when you have, say, if you have 90 rows, maybe you should have only 3 features. So for every one feature, I will have at least 30 rows. Keep that rule of thumb, right? And violate it only if you know that you're violating it intentionally and you will not overfit. And again, this is an advice for those who need it. If you don't need it, if you know what you're doing, by all means, you go ahead and do what you want to do. Once you get this small data, try not to overcomplicate. If you want to find the value of just a single data set, it's not worth overcomplicating it. And maybe just look at the level, change and z-score, right? What happens when you overcomplicate? The chance of overfitting is almost exponential. When will you overcomplicate signal generation? When you triangulate one data set with multiple other data sets. Right? So suppose you're evaluating different data providers, data provider 1, 2, 3, 4. They give you a bunch of data sets. You want to compare them. Do something simple. It's not worth doing something more complicated at this signal generation stage. When you triangulate again, then put your random forest and other stuff. That's the lesson that I see. I see mistakes being made at both these places, which is why I put this slide. Okay. What can machine learning do for a quant? There's so many courses on machine learning, and I'm sure many of you have done multiple courses on this, but I haven't seen this slide anywhere, and that's the reason I put this together. I think there is so much value in it. So in very simple stuff, the dimensionality reduction is such a simple idea that is still very useful. We have known for 20 years that if you take the yield curve, you do PCA, you get 3 factors: level, change, and curvature. There's nothing wrong with it. It's still valuable in a lot of in use cases. If you think of portfolio construction, you can recursively cluster, make a Huffman-like coding, do equal marginal wall. That works very well. This is called hierarchical risk parity. Again, nothing fancy, but still very useful. Feature selection, like my previous speaker mentioned lasso, right? Again, understand it in a financial context, right? Okay, if you're a mathematician, I tell you, hey, you had a loss function, your error term is your norm, and you're reproducing kernel Hilbert space, and you understand it, right? If you're a Bayesian, I tell you, man, this is just a Laplacian and Gaussian prior on OLS, you understand it. But if you're a finance guy, you don't need to be intimidated with this jargon, right? You can understand it in a very simple way. Somebody did a linear regression, he took a stock, and he gave you a very simple linear formula. He said stock is equal to, say, 20 times SPX minus 19 times global equities. And you look at the numbers and say, hey, something is off. 20 times S&P minus 19 times global equities, maybe they cancel each other. If you trade it directly, it will be an unreasonable amount of leverage. It's probably not even tradable. So then you say, hey, lasso can prevent this. If I do something like lasso, the weights will come down. And that's what lasso is. Right? The point, again, is actually quite simple. You don't need very complicated explanations for this. There's a financial intuition that can come. And that's what lasso and ridge in all of them do. The third point is the interaction term. I have a bunch of columns in Excel. I used to do my linear regression, but it turns out that column 1 divided by column 5 is what is more important. Maybe column 2 multiplied by column 7 is more important. These very simple interaction terms that I had to explicitly account for, it's what support vector machine with the radial versus kernel does. And it turns out to be quite useful, right? And we were trying to improve some short wall strategy previously, and so we took a bunch of terms about the wall surface, bunch of terms about interest rates, did some very simple PCA, then realized, okay, there's a bunch of interaction terms that I need to account for. Let me account for PCA and SVM, and it works very well. The catch there is not in the algo by itself. The catch there is in the fact that short wall works very well till it doesn't, right? XIV falls from 120 to 4. You don't want to be caught on the wrong side there. So the catch is somewhere else. Catch was not in the algo by itself. The last part is the replacement of if-else loops, right? What's the problem with linear regression? The problem with linear regression is, let's say you want to regress equities with inflation. Moderate inflation tends to be good for equities. Very low inflation is bad. Very high inflation is bad. The two extremes don't work very well. And that's why linear regression doesn't work. In very simple stages, I need an if-else loop. And that's really what we do, right? You say, hey, Rajesh, if price momentum is positive, if my EPS momentum is positive, but my valuation is less than the median, then I'll buy it. So you made an if-else loop. If you make an if-else loop, why not make different if-else loop across different historical periods? Why not make different if-else loop using different explanatory variables? You do them both, you get bagging. It's called random forest. And that's what random forest is, right? It's not that m equal to square root p formula that you see, or it's nice to know. If you look at the Chen and Guistrin paper in 2016, it has a nice formula. Read that. But have an intuitive sense of what it's all about, right? You have a mathematical sense, you have a financial sense that's actually quite simple. What's happening here? This is, there's a fear of missing out that is driving massive amounts of hype, right? All of us have seen this. This is, and I'm using words that teenagers use, like FOMO and other stuff. And like 2015, people were completely skeptical about alternative data. They used to say, what will I do about it? And now I see multiple people have first buying a data set, then not knowing what to do with it. This is crazy. You are sold a data set because the data provider could not trade it by himself as a hedge fund strategy, right? So why do you expect that just one data set will give you a magical sharp? It cannot. It is, it's like a lottery ticket. I know it's going to give me 1 million, but I still sell it to you for 50K. It doesn't work like that. The reason that people sell you is it's viable in a portfolio context. You take that data, you make a strategy, and you say, okay, my correlation to value, growth, quality, size, beta, carry, whatever it is very low. So it's viable in a portfolio context. That's what, right? This close is an acronym that I coined last time I was here, Armando. Last year when I was here with Marco, something I wanted to make one cheesy acronym to say, how do you evaluate data sets? So C there was when you look at data set, C was the number of assets that you have to cover. How many assets will this data set comment about? L is the length of history. And by practice, okay, if I'm looking at sentiment data, maybe I can get a longer history. Maybe if I look at satellite data, I can get only a shorter history. If I look at credit card data, I can get, let's say, so many years of history. Know that. O was the orthogonality. I stressed that orthogonality again and again, right? Use the fact that this data can tell you something orthogonal to what your accounting metrics can tell you. Yeah, a car count is telling you something that the accounting metrics did not tell you. Quite believable, right? The S was a Sharpe ratio. Do simple analysis, level change, z-score, get your Sharpe ratio metric. Don't expect magic. Expect a 0.6, 0.7, 0.8 value. If you get 1.2, maybe you'll pay a lot more for it. E is, can it enhance your fundamental thesis, right? Ravenpack data, let's say you're looking at new sentiment data, maybe it can help you avoid a value trap. Maybe it helps you avoid a cognitive overload. You have so many stocks, you can't monitor all of them. New sentiment data spikes one stock, then you can go and dig in. Maybe it helps you avoid cognitive overload. The next one is, this is a mistake that I see. Don't jump into the deep end of the pool in the sense that, maybe you are okay with getting a report on a data set. Start with that. Next, you can look at the raw data and do some analysis by yourself. Next, maybe go into the granular data. And there's value in going to granular data because aggregation often induces errors. But even there, do you really need to go and access an NLP parser and try to do NLP by yourself? It's not reasonable. You need not do so. You can as well rely on somebody who is giving you access to an NLP parser and then do so, right? Unless you want to learn Common Lisp and compete with more professionals in this place. And again, the last point is the excessive focus on NLP. I mean, what looks crazy to me is I see a bunch of people who know linear regression, and then they tell me they want to do AI. Why would you jump from linear regression directly into AI? That's so far away, right? You don't have to jump like this. There are a million things that are there in between, and we, as reasonable people, it behoves on us to do so. And know the limitations, right? Vinograd schema, the antecedent of an ambiguous pronoun is not known, and most of you know it. If you haven't seen it, just Google it up and see. So know the limitations of what needs to be done. AI, this is the exclusive focus on NLP or on unstructured data. It actually harms us. Technology companies do it because their data is naturally unstructured. We have a ton of structured data that we haven't looked at as much as we could have, right? And if you look at the classical risk premium, what are they? You take a bunch of accounting parameters, do long, short, beta neutral, dollar neutral, industry neutral. It's all very simple arithmetic. A million things can be done to improve it directly. This is an interesting point. This is big data may not ever be very powerful for macro. This is a very interesting claim that I've been making, and some people get angry at it. The idea is that big data is not completely new. Right? Beginning in 1920s, Wesley Mitchell was collecting large amounts of data. This is when Simon Kuznets made his curve. He even got a Nobel Prize for it. I think it's 71 that he gets it. This idea of collecting a massive amount of data, which tells you the micro story, and trying to aggregate to make the macro story, has a long and celebrated history, unfortunately not very successful. And this is what both Keynes and Hayek were criticizing, right? Keynes and Hayek disagreed on everything else. But they said, hey, look, you can't make a theoretical model to explain the economy. You can't make atheoretical statistical models. They do not work. That is what Paul Samuelson's attempt was in 1950s, called the neoclassical synthesis. Take all my micro big data, take my macro, add it up, and connect it with a nice theory. It didn't work, right? And people got a lot of Nobel Prizes for doing this stuff. Klein and Ragnar Frisch got the first Nobel Prize in '69 for analyzing this. Jan Timbergen and Ragnar Frisch get the Nobel Prize in '69. Klein was leading the Wharton Link project. There's an MIT UPenn project. Take hundreds of thousands of variables, hundreds of thousands of data points, add it together, try to predict inflation, and then fail magically. Then you have the Lucas critic in '76. It's all about saying this thing, you should always use big data. Use micro foundations. That's really what it means. Saying use big data. That's what will save you in life. And it didn't work. But very simple things work. 1970s saw what we call the Box-Jenkins approach, right? Your R-Magarch approach and other stuff. They're very useful. If you haven't looked at it, look at what's called Box's method. You can go to David Blake's website at Columbia. He has a very interesting Bayesian interpretation. There's a modern Bayesian version of what we used to do in the frequentist world. And then, of course, you have the Bayesian attempt by Chris Sims. He also ended up getting a Nobel Prize in 2012. He wrote this paper in 1980. Quite useful, right? We did this stuff. If you got your PhD in 1980s, you probably made your own Garch model because that was the fad of the day, and it's just there. And magical models have been made. Even if you're an economist, you read the 2004 paper by Smet and Wouters saying dynamic stochastic general equilibrium model, very complex. They finally don't work. That's and whenever you want to criticize something, you say there's hegemonical control of micro foundations. That's what Oliver Blanchard said. He's the ex-IMF chief. Point of telling you all this is, big data tells you a micro story. What you want is a macro story. When you want to comment about sectors or rates, it's very, very hard to do so. This might be a fundamental limitation. Statistical physics does not really add up to physics at very long distances. We know the game in biology where microevolution and macroevolution are still not very well coupled. And this is the story of academic macro. You have a separate central bank macro, an industry macro. That's actually an interesting point. If you go to Wikipedia, they tell you economics is salt water, fresh water. It's actually academic macro, industry macro, and central bank macro. This is your academic macro story, which tells you it's not possible at all. You do get some data, of course, and let's not dismiss it completely. You guys already know MIT Billion Prices project for inflation. You probably know satellite images for commodities. You know all the data that the intercompany payment data for credit and other stuff. Okay. So what is data science? Again, very simple. It's physics doesn't say physics science, chemistry doesn't say chemistry science because it's actually a science. Social science says social science because probably it is not a science. Then is data science a science? It is probably, maybe I'm doing some fraudulent work at work. So how do I justify myself? You say, hey, look, data science is still more of an art and a craft. It's not a rigorous procedure. And it is not just machine learning. This is just unreasonable to expect. Look at statistics, for example. How do you combine intuition with data? When you talk to a fundamental guy, he says, hey, I have a lot of intuition, the leap of faith beyond facts that I call intuition. How do I combine with what the data says? You tell him, well, Bayesian techniques you can do. No, it's not new. You can do it informally in the form of a black Litterman model, or even other ideas. Take bagging and boosting, that comes from statistics. Take your L1 regularization that the previous speaker was using, that comes from statistics. None of those values, things have gone out. Take signal processing. You don't have to do AI. If you're doing ordinary linear regression, your beta is wrong. You can change to a dynamic beta by using a Kalman filter. Hodrick Prescott, I don't like it, but people seem to like it, so you can use it. Hidden Markov model have been known since 1989, since Rabiner's paper. None of them have gone out of fashion. You don't like Kalman, use particle filter. Again, use the things that are practical. I'm not saying use Kramer-Rao-bound right now, but you can use things that are useful. Right? In econometrics, again and again, people say, what happens? How can you how can you separate causation from correlation? Right? Yes, it's not an ironclad thing, but have they not heard of Granger's causality? It doesn't work that well, but it's there. Right? Not saying you have to look at Julia Pearl's work, and I know the limitations of it, but these are not questions that we have never handled. The way that people ask, saying, okay, has it never been done? No, of course it has been done. Once you look at all three, then you can look at machine learning. By all means, look at machine learning. Do as much machine learning as you want, and I'm with you. But there's no need for you to exclusively do machine learning and call it data science. And that's the point, right? Do we know how to combine it? I don't know. There's a nice textbook by David McKay written a very long time back. He's not alive anymore, but there's a last serious attempt at integrating all these aspects and putting them, making a grand theory, maybe using information theory to explain all this. It doesn't exist. We don't have it, right? And our theoretical knowledge is still very weak. For example, if I'll refer to that in the next slide, so let me skip this. Okay, let me give you some takeaways, right, before I end. Quant today is more open than ever. It's not a hidden secret. There's no magical. We're not making one magical strategy that will run forever. It's like making a car. We know how a car is made, but you're still making a car factory, and running it is still very hard. Nobody takes away credit from anyone for it. You don't have to implement hidden Markov model yourself. Please use sklearn. If you're doing Bayesian stuff, look at something like PyMC3 or Edward. A lot of it is there. What's happening is view machine learning as an art of locating new, nonlinear, ephemeral risk premia in a dynamic fashion. Relentlessly, I have this data. I don't have to all use Axioma and Bara and create crowding nicely. I have this data set. I can combine them in a million ways now, non-linear ways, everyone in a different way. It's like I let 1,000 flowers bloom. So you can do that, right? That's really what it is. Of course, it won't be a static alpha running for a long time. It will be dynamic. That's OK. The next one is crazy, right? If I go to a machine learning conference and talk about Lasso, all my friends in computer science will laugh at me, saying Rajesh has become stupid. Because it's trivial, right? Lasso paper came in 1995 by Hasti Tifshirani, you know that. The Brayman paper was in 1992. But there are some newer things. The XGBoost paper was in 2016. But the reality is I have very low SNR. I have to use extremely simplistic models. So it takes a certain amount of confidence to say, look, all that I can do is Lasso. It's as embarrassing as it is, but that's all it is, right? But what point does it become simplistic? If I'm using k nearest neighbor sometime and maybe I'm overfitting, then yes, right? And this is your thesis and antithesis in this Hegelian dialectic scheme. Very strong model of linear regression. The other end is k nearest neighbor. Both of them sound beneath contempt. They're so simple, but they need not be. If that's what it is, you do what you have to do, right? Where do you use machine learning then? Well, there are a ton of inherently nonlinear tasks where your linear things don't work. Maybe you have some macro factors, oil, dollar, gold, economic surprise index, EGX, IG, HY, and you want to rotate between 10 factors. Yes, there is some relation between the macro factors and your sectors. And yeah, I can believe there's a nonlinear relationship. You can try random forest there maybe, right? You want to make a portfolio construction scheme. The example I gave you, we know the shortcomings of each of them. Try hierarchical risk parity. That seems to do very well. I also gave you the example of short wall timing. I have a bunch of accounting parameters. I want to decide when I will go long wall, short wall, or when I want to see when call overwriting beats the underlying beta index. My delta is less than 1. Maybe it beats. Maybe it doesn't beat. Very simple quasi-linear stuff you do. The last point will irritate a few more points. No neural networks yet at daily frequency, and they look at me and saying, Rajesh doesn't know AI. Do you know adversarial training? Do you know K-shot? Do you know weight decay? Do you know regularization? All the nice stuff that has come out. The thing is, you don't have enough sample points. You could try to fit a universal model across stocks, but that's unlikely to exist. I know there's a paper 2 months back by Rama Kant that made the claim. But even otherwise, as far as I can see, again, this is advice for those who need it. If you know what you're doing, and if you say, I really understand what I'm doing, I know how dropout regularization works. I read the paper by the Google guys last year who said, we need to rethink generalization for deep learning. You read the repost by Joshua Bengio in July 2006 on that. You know that stochastic gradient descent is an implicit regularizer. If you know all that, you don't need me here anyway. So then, yes, please use the neural networks at daily frequency. If you did not know this, don't go and do it. You will probably overfit. There's a nice asset manager in California who wrote a paper paper on how to use neural networks to predict recessions. You have 10 sample points, man. And the other model was a ranking model. So in that same paper, he has ranking, arithmetic ranking. The other model is neural networks, and a big asset manager. Anyway, so now what is to come? This is one tiny example and one very big example, right? People talk about technical patterns. I'm quite curious if CNN can detect technical patterns. I took a shot, I couldn't do it. I see some posts online, but not very satisfactory. But maybe if CNN can find whether a dog or a cat, what it is, maybe it can tell you, maybe we'll expose the technical patterns work or don't work, we'll find something. Strategic, deep reinforcement learning. Again, people are going to shout. They'll say, hey, it's already there. I do it. Well, it turns out, as a researcher, I can tell you reinforcement learning is in the research stage. It is not a solid product like the other things are. It's good to be interested in deep Q learning, but the places where it's used is still limited. But it's still worth thinking about it, right? And I believe there's some other talk so they can talk to you about exploration versus exploitation. They can talk to you about credit assignment path. They can talk to you about all the million things about deep Q learning and Keras-RL. So I'll skip that. But the point is there is something very interesting there. Do not dismiss it completely. Do not jump in with both feet into the water into it. But there is something that needs to be investigated, and hopefully with time we'll find some nice developments in that field. That's all from me. Thank you very much.
This is Raven Pack.